We'll start the second and last session of the afternoon. We are very happy to welcome Evgenii Kuznetsov from Moscow. Evgenii, can you hear me?
Yes, I am here.
Great.
Hi, Pierre.
So welcome. So you can start.
Yeah, okay, thank you very much. So I would like to thank, first of all, organizing for inviting me. So I'll speak about nonlinear dynamics of sleeping flows, and this work was done in collaboration with Evgeny Mikhailov from Physics Department, Moscow State University. So the plan might talk is large enough, but however, it's necessary to explain first of all what does it mean sleeping flows, and it's something maybe new for many people. So sleeping flows in fact it's a very simple flow along rigid body, but in viscid case. So you have no viscosity at all, and therefore you have only one boundary condition when the normal component of velocity is equal to 0 in such a case on the surface, and you have only longitudinal velocity. And it turns out that in such a case, such a flow has some peculiarity connected with the compressibility. And this compressibility results in appearance of folding or maybe sometimes gradient catastrophe. And probably it's a main issue of my talk. So I will speak about two equations. It will be two-dimensional Prandtl equations and three-dimensional Prandtl. In both cases, I'll show that you have an appearance of singularity in a finite time, and you have a break-in, the usual break-in which we know in gas dynamics, in spite of incompressibility conditions. So you have incompressible fluids, but however, you have a formation of singularity, you have a break-in. And this break-in appears due to the boundary only. And it's a very crucial point. And I speak also about two-dimensional Euler case. And in such a case, I show that there exists also growth, exponential growth of velocity and vorticity gradients. And it's also quite interesting because of it. It's somehow there exists the topic more or less the same. But it happens not in a finite time, but you have only exponential growth. So the question whether finite time singularity develops in ideal fluids is still open question in spite of certain progress in both numerical and analytical studies. And in our papers, so you can see here a lot of papers in collaboration with Prandtl and Lebedev. And we demonstrated that for 3D Euler equations for periodical boxes, we have observed formation of high vorticity structures of the pancake type, with exponential growth only, but without any tendency to blow up. It's interesting. But if you have a rigid boundaries, reason one is both demonstrate blow-up behavior. So, for instance, for two-dimensional planar flows in the region with non-smooth boundaries, Kishelev and Zlatas prove blow-up existence. So you have a two-dimensional Euler equation, but you have non-smooth boundary conditions. This means that you have some, I don't know, cusp or maybe angles, etc. And in such a case, they prove theorem about blow-up existence. The most important point is numerical investigation, numerical investigation by Lu and Howell for axisymmetrical flows with swirl inside the cylinder of constant radius. And they observed appearance of collapse on the boundary. They obtained appearance of vorticity on the boundary. In fact, it was a challenge why boundaries play so important role in formation of singularities. And later, two guys, are written here, prove the existence of soliton in axisymmetric flows, but outside the cylinder, and with some angles there. And so the latter result somehow correlates with the studies of Kishilov and his co-author for two-dimensional Euler equation inside the region with non-smooth boundaries. And it's necessary to say, because if I will speak about Prandtl equation, it's necessary to mention the work of E and Inquis, which showed rigorously results about blow-up existence for both inviscid and viscid cases. It is some partial solution, but however, it was something important and interesting. It's necessary to say that in 1980, the blow-up appearance in the Prandtl equation was observed in numerical simulation by one Dumoulin and Shen. And it's a very interesting paper also. Another paper by Honk and Hunter, and they investigated this problem for both, and in particular, they demonstrated that singularity can appear on the wall for inviscid case. So another paper also very interesting. It's a paper by Kishilov and Shverok for two-dimensional Euler equations for flowing inside a disk. They found constructed, in fact, some initial data for which the gradient of artistic exhibits double exponential growth in time. Not usually exponential, but double exponential growth. And it's a very interesting situation. Simultaneously, the velocity gradient grows on the boundary exponential in time. So in this talk, we show that the flat boundary itself introduces some element of compressibility, just what I mentioned already. So I consider two cases, two-dimensional and three-dimensional inviscid Prandtl equation, and two-dimensional Euler equations. Let's start from the Prandtl equations for two-dimensional flows. It's written here. It's equation P here is a given function of x, depending only on x. It's a Prandtl approximation. From Prandtl approximation follows immediately that what does mean Prandtl approximation? Prandtl approximation means that the characteristic size along boundary much larger than the thickness of boundary layer. If you assume, then it follows immediately that you have a such type of equation, and P in here can be found or can be defined by the usual Bernoulli law, which is written there. Well, it's necessary to say that in Prandtl approximation, it's possible to introduce the phaticity. So omega is equal minus du dy, and omega is satisfied with the same equation as for two-dimensional Euler equation. So it's also, so omega in such a case is Lagrangian invariant by the theorem itself will be bounded for all time. However, for another component of the velocity gradient, such restrictions are absent, and we have formation of singularity. So what's important? If we come back to Prandtl equation, it follows that if Px is equal 0, so for constant pressure, in static case, you can see that U is nothing more as a Lagrangian invariant. And now let's consider what will happen if we consider the usual Lagrangian quantity in two-dimensional incompressible fluid. And so n is some Lagrangian quantity, and then let's know that you have some solution n as a function of x and y. So if you consider inverse function, it looks like as some in fact Legendre transformation. Then it turns out that it's possible to get that. Oh my God, it's something wrong in my, okay. You will get the equation which is written down. And it follows that you have equation which, in such a case, you have a y as a function of n and x, n and x and time, and then you have equation which is well known for free surface hydrodynamics. And important point is the following, that if you introduce the trim function and then expressed in terms of density n and x and time, it follows that these equations for density, in fact, for Lagrangian, can transform in a linear relation also, and it's a very important point. So in fact, we have a non-linear equation somehow, but however, after such a transformation, this transformation is nothing as a Crooked transformation in this case. And it's possible to resolve this equation by introducing generated function. And then, for instance, for inviscid Prandtl equation, it's necessary to write down that u can be expressed as a stream function. And if you now introduce this relation, it's possible to get that theta u, it's a derivative with respect to u, satisfied to this very simple equation. So it's a solution is written here, and after that you have a solution of this equation in the form of integral. So one can see that you have a two constant, two some function, but the most important point is the following, that f is nothing more as consigns with the velocity u on the boundary, and z is equal 0 completely. But what's important? Important the following, that at y is equal 0, you have a Hopf equation, and Hopf equation has a blow-up behavior, right? It follows immediately. Derivative du dx becomes infinite in infinite time if this derivative use a 0 prime of a is negative. And in such a case, we have a solution up to the end and can demonstrate what we have. The most important point is the following, that if you now analyze what will happen on the boundary, it turns out that if you introduce the usual tau star, it's a time of appearance of gradient catastrophe, and a star also, then after that you can see that you have a such type of behavior near singular point for derivative. And it follows immediately that in such a case you have such type of self-similarity. Delta E is proportional to tau in half, but if you come back to the physical space, to x variables, it follows immediately that x in such a case will be proportional to tau in 302. So this means that in x Lagrangian space you have some compression of this region, but in a physical space you have a more rapid situation, and it turns out that you have a such type of behavior near the singular point. The most important point that maximum ux in such a case will be proportional to L minus 2/3. L here it's a width. It doesn't this as so doesn't contain the time dependence. It's very important, and this is in fact the sequence of gradient catastrophe only. So you have a folding, and independently whether singularity happens in finite or finite time or infinite time, it doesn't matter. You have such type of relation, and it's a very important. Okay, so in the case when you have a general situation, then in such a case, the solution can be solved rigorously, because in such a case you have a Newton equation which can be integrated, and after that you can analyze everything what you need. The most interesting point is the following, that if you consider now the derivative omega x at the boundary, it turns out that you have such type of equations. These equations can be solved using the method of characteristics. It follows immediately that d omega dt will be equal minus ux omega x. But ux in such a case, when you have a blow-up behavior, is negative. And then if you integrate this relation, it will immediately that omega x behaves, you have the same behavior like for derivative of velocity. Now it's necessary to say that there was many numerical experiments which I measured also the Domelin and Shen, Honk and Hunter, and they obtained the same results: the formation of blow-up behavior in inviscid case, and formation of jets in perpendicular to the boundary direction. And it's a very interesting point. And it's necessary to say that the same phenomenon which we obtain also for two-dimensional Euler equations. And in some sense, we developed the idea of Kiselyov and Shverok about two-dimensional flows inside a disk, and we demonstrated that we have the same behavior like for appearance of so what we solve numerically? We solve it numerically for equation for vorticity for such initial conditions, and this our initial conditions, and what we obtain numerically. We obtain numerically the situation is very familiar to that which you have at y is equal 0, so on the boundary we have such type of behavior. So you can see the tendency to appearance of large gradient. Moreover, if you consider how you x depends on x at different times, so you can see formation of cusp here. So you have a very large gradients, and we establish that if we consider how the ux expressed in terms of L, it turns out you have a such type of dependence, and it's a very close to theoretical prediction for Prandtl equations. For Prandtl equation, we have just the same situation takes place here, and we checked it here numerically. And the most important point is the following: that when you have a formation of folding curve, you have a jets in transverse direction. So you can see that here are the jets, and it turns out that these jets becomes narrow and narrow in time, and so it's a very interesting point. And another point is the following: that we establish also how the gradient of vorticity behaves in time. It's equation at y is equal 0, so it's necessary to differentiate this equation with respect to x, and then consider the limit y is equal 0, and then it turns out that you have such type of equation for characteristics. It follows immediately that d omega dt will be proportional to such type of integrals, and this means that omega x, if ux increase exponentially in time, then you can see that you have a double exponential increase. So in some sense, what we obtain numerically, it's just a result of our numerics. We can show that you have more or less double exponential growth for vorticity gradient. Another point which I want to consider also, I have maybe 10 minutes or maybe something like that. I consider the question concerning breaking in three-dimensional inviscid Prandtl equation. So it's an equation for you. You here it's a two-dimensional vector with the components x and y, and we here it's a velocity perpendicular to the boundary, and we have again minus gradient p. P of r is a given function. This equation is nothing more than incompressibility conditions. And then it follows immediately, if you consider the limit v is equal to 0, then we arrive at the equation of the same type as it was before. But the difference is the following: you here, it's a two-dimensional vector. So we have in three-dimensional situation, if you consider slipping flow, for slipping flow, you have such type of equation. Of course, it can be soft. It's not a question. It follows immediately by using the method of characteristics. But I would like to show how this equation can be easily solved if you consider the situation when the pressure is a constant. In this case, it's necessary to introduce the velocity gradient. So it's a capital U standing here. And if you differentiate our equation for p is equal to 0, and it turns out that you have a very simple equation. But you here, it's a matrix 2 by 2. And ddt is nothing more than material derivatives. This equation can be solved easily because of it, because of u standing here, and it will be the answer. So u0 of a is initial position or initial values of capital U, and a here is initial values of position of fluid particles. So you have an answer. And then how it's possible to analyze this formula? It's an interesting point in the formula. Let's expand our initial values u0 of a in terms of projectors. So projectors corresponding to different value of lambda alpha. So you have only two eigenvalues in such a case, and then you can see that in denominator you can get some singular behavior. So it follows immediately if you have such a time, so lambda alpha in such a case must be negative. In such a case, in future you have a formation of singularity. But in principle, because of to find eigenvalue in such a case, it's necessary to solve a quadratic equation, so as well known, and in principle, sometimes so it's possible to define the condition when lambda alpha is negative. And the most important point is the following: that near the time t is equal to 0, you have a singular behavior. The same singular behavior which you have in one-dimensional situation. But you standing here, it's a matrix. So it's this matrix. This means that you have a singular behavior not only for stress tensor. So stress tensor it's a symmetric part of this tensor, but also for antisymmetric part. Antisymmetric part is nothing more as a vorticity. Interesting point is the following in such a case. What we have? We have a very important conclusion, in fact. Let's imagine that you have a blow-up behavior. And how it's possible to understand what is the physical appearance of such type of singularity for sleeping flows. In fact, in two-dimensional situation, in two-dimensional universe, you have two counter-propagating flows. And in some sense, you have a scattering between them, which results in the appearance of jets in perpendicular direction. It's a very important point. So, of course, in such a case, everything is okay with an incompressible fluid, but you have a compressible character for sleeping flows. The second point is the following. You can see if you in three-dimensional situation, of course, you have to get the same situation more or less. You have a formation of jets in perpendicular direction, but simultaneously vorticity can be infinite large. So you have the same gradient catastrophe. And this gradient catastrophe results, in fact, in two very important ingredients. The first ingredient is the following: you have a formation of jets in perpendicular direction, and you have a vorticity. But vorticity itself characterizes that you have some rotation. It's possible to demonstrate analytically that if you have a vorticity, then it turns out you have some rotation. And this means that you have a tornado type behavior. So you have a formation of very small region, very small region, you have a compression, and then you have a formation of jets in perpendicular direction, and also you have a rotation of this region. And so it looked like as a tornado. So in some sense, for three-dimensional inviscid Prandtl equation, it's possible to say that this is a phenomena which can explain probably appearance of tornado in nature. But the most important point that physically appearance of such type of singularity comes from slipping flow. Or you can ask me, okay, in real situation it's necessary to take into account viscosity. But viscosity, we know that at higher Reynolds number, you have a so-called viscous sublayer. If viscous sublayer is small enough above them, it's possible to think that you have a almost inviscid flow. If it's so, then it turns out that you have to get formation of tornado type phenomena in usual hydrodynamics. So now conclusion. So, in fact, we have developed a new concept of the formation of large velocity gradients with a blow-up behavior or with exponential in time increase with the slipping flows in incompressible inviscid fluids. And these processes develop as a folding due to compressible character of the slipping flows. So it's a crucial point. So in some sense, we found in spite of incompressibility of fluids, then it turns out if you have some consider only slipping flows, it turns out that the slipping flows is a compressible flows. And what we demonstrated also? We demonstrated also that for two-dimensional inviscid Prandtl equation, we have developed mixed Lagrangian Euler description, and it's a description that corresponds to the so-called Crocker transformation. Crocker found this transformation in 1939, seems to me. And application of this description to inviscid Prandtl equation allows to construct solutions. Also, it has demonstrated that for the inviscid Prandtl equation, appearance of the finite time singularity can happen on the wall. It's a very important point. For the Euler flows, for two-dimensional case, we have numerically found that maximum of velocity gradient is developed on the plate with exponential increase in time. Simultaneously, the vorticity gradient has been shown to demonstrate a double exponential growth in time on the boundary. So, I finish. Thank you very much for your attention.
Thank you. We have time for one question. A question. I have one question. It's not completely clear for me. What are the boundary conditions that you have used? I imagine that in the 2D case, you have the slip boundary conditions on one direction and maybe periodic boundary condition on the other side or something like that.
No, it's not necessary because of the main, if you have in viscid case. In viscid case, you have only one boundary condition for normal component of velocity. It vanishes, and that's all. And this means that two other components of velocity are free. It's a crucial point. So you can reduction of your flows or three-dimensional flows to the boundary. And if you consider such a reduction, it turns out you have a two-dimensional flows. And these two-dimensional flows becomes compressible. In spite of incompressibility of fluid. So when you have a compression, then it results in appearance of jets in perpendicular direction. So if you have you have in some sense, what you have? You have a scattering of two beams or two flows, and then it results in appearance of jets in perpendicular direction. And simultaneously, it's a very important point, simultaneously in three-dimensional situations, at least for three-dimensional Prandtl equation, you have a blow-up behavior for vorticity. And therefore, it looks like as some tornado property for Prandtl equation. Of course, for three-dimensional Euler equation, it's open questions necessary to perform numerics, etc., etc.
Okay. Thank you very much. Thanks again, Evgeny.
Mm-hmm.